Actually, just submitting your solutions. I mean, the prediction. Your task is to predict the income level. You just for example, download test data and just submit your prediction, and it will.
So you're allowed to use like other languages.
You're allowed to use any language.
And for the code competition, are we supposed to use like code we write like for assignments, or are we allowed to use like sort of like established machine?
You can use whatever machine learning libraries. You're actually I'm not highly encouraged to implement everything from scratch for that, because the cross project, the goal for cross project is to help you to have a like sense how to apply machine learning practical things, right? And in practice, you know, no matter you're doing some industrial applications or doing research applications, you really need to like implement everything from scratch. You do not need to reinvent the wheels, right? But for course assignment, it's different, because our goal is to understand mechanism. You won't capture the mechanism until you implement something by yourself. This is different.
And so another question, so will the assignments build on each other, or is it like, for instance, okay to like do one assignment in one language, do like another assignment in a different language?
I don't think they are building on each other. Probably they share some data sets. That's possible. That's just to, I mean, we do not need to download data set again, right? But usually the tasks are independent, and you can choose to implement the decision tree with Python and then boosting or bagging with C++. It's up to you. But as I suggested previously, right? If you use C++, you need to spend more time and be more cautious about all kind of low-level issues like memory leak, right? You know, segmentation fault if you use labeling system. Any question? Any other concern regarding the course project?
This is regarding the assignment.
Uh-huh.
I've seen that some implementations, when it deals with like real value, people use something from like a card model, like calculates like a final test binary split, like the optimal point to split like a real value.
Oh no, we're not doing that one. You can, I think in our whole assignments we have given you the strategies to do the split. If you want to do that, you're very welcome to do that, but it's not obligatory. Actually, if you guys like can implement everything indicating in the assignments, I will be very happy, because I heard complaints that the workload is really high about that. But if you want to do further with it, that's fantastic. Any other question? Oh, great. So yeah. So keep an eye on on deadline, and please start to think about what kind of project you want to do and what kind of team you want to form. Of course, if you do the CAD competition, you have to do it by yourself. Okay. So let us continue with the computational learning theory. So in last lecture, we introduced a few key concepts in computational learning theory, right? And we mentioned that several important goals in computational learning theory. That is how we quantify or bound the generalization error of a particular learning algorithm, right? So in order to do that, we introduced the so-called generalization error, right? So to define generalization error, we need to respect that our data are random. This is actually consistent with real world, right? So you cannot assume like your real world is deterministic. On the contrary, the real world is filled with uncertainty, right? So we assume that our training data and also the test data are drawn from some very complicated unknown distribution D. Right? We just denote it by D, but actually in 99% of cases we do not know what is D. D is very unlikely to be Gaussian or T distribution or whatever. Probably D doesn't have any analytical form. It's possible, right? And then only when we have this, when we assume that there is a distribution D over the examples in the whole instance space, we can define the error of a hypothesis. So here, hypothesis means the outcome of your machine learning algorithm. Right? If you run machine learning, if you use decision trees, then the hypothesis could be the decision tree constructed from your ID3, right? Or if you learn linear classifiers, that could be a linear model, whatever. Right? So, so we define the generalization error of a hypothesis H with respect to the target concept F. Namely, we always assume there is some kind of ground truth function which maps the instances and the correct labels, right? And we define the generalization error as a probability that for an arbitrary example, which is sampled from data distribution D, the chance, the prediction made by a learned hypothesis is inconsistent with the prediction made by the ground truth. So basically, what is the probability that you make a wrong prediction of your learned hypothesis with your learned hypothesis under this data distribution D, right? So this is the definition of the generalization error or true error. And we also discussed that actually this kind of value this metric is objective. It's there, but we're rarely able to obtain this value. Why?
We don't have access to it.
Yeah, that's one reason. Is there any other supplement? Mm-hmm.
We can't get a value for every point. We just sample some distribution.
Yeah. To be more explicit, we actually do not know the form of D, right? So we have to sample. We only have to sample. That means we can never remember to compute this. This is essentially to calculate some integral over the probability. I mean the distribution D with this indicator, right? So if you follow the rigorous definition of this probability to compute this probability, you do not have access to that, and you do not have access to the distribution D. So that means okay, you can only estimate, right? So the most common methods which we use it by default, but probably less people are thinking about the nature of that, is to draw samples independently. Like we draw 1,000 samples and just count how many examples are incorrectly are mistakenly classified by our age, and we'll go like 20%. Okay, my true error is estimated to be 0.2, right? But it's not guaranteed to be 0.2. Remember, this is just the estimation. But in practice, how can we? In addition to estimating this true error, what other errors can we get, right? So the most common used error is called empirical error, right? So empirical error from this lengthy definition is just means training error. Namely, like when after the training, I just use my learned model H to predict every training example and count the proportion that the proportion of the misclassified training examples, right? This is called training error or empirical error. Right? So with this definition of these two errors, we can give a more formal definition of overfitting. Namely, when the empirical error is substantially lower than the true error, then your machine learning algorithm kind of overfits the data. Right? Like, for example, if your empirical error, namely is on training data, right, is 0.01, very, very accurate. Right? But your test error is 0.2. That's a giant gap, right? That means, okay, perhaps you overfit the data. Some noises in the training data misled your learning procedure, then end up with some imperfect classifier. And then we talk about how do we use some mathematical language to rigorously characterize the performance of your machine learning algorithm, right? So we cannot use a deterministic claim. We cannot say, okay, I give you a super powerful decision tree. I guarantee you my decision tree can produce a classifier. The true error is always 0.1 or 0.01. It is infeasible. Why?
Depends on the sample and its rules. In instances, for example, it's a probabilistic method.
Yes. Yeah. Remember, in real world, our data set are random, right? So this time you draw like 100 perfect examples which are highly representative of the whole adjacent space is possible, right? And then you throw it into your decision tree or deep neural nets. It may end up with very good model, right? But next time when you draw another 1,000 examples which are really bad,
No, the camera is full.
what?
The camera.
Probably you can fix it there. And next time, if you have very bad quality training set, you cannot expect the performance of the learned model is very good, right? So that means the performance of your machine learning algorithm is not only dependent on how smart the learning procedure itself is, but also dependent on the input, the quality of the input. The consequence is that we can now use deterministic language to claim the performance rate. Why? Because it varies along the input, right? Garbage in, garbage out. Remember, machine learning is always data-driven, right? If you give a garbage data, you cannot expect it outputs gold. So the realistic way to claim that or characterize that your specific machine learning algorithm is good is in a probabilistic way. We can give a small parameters epsilon and delta, which represents the level of the error and level of confidence. We see that if our learned hypothesis with probability at least 1 minus delta achieve the generalization error at most epsilon, then we'll say, okay, your learning algorithm is good. This is the key idea. So that's why we have to, in the computational learning theory framework, we always use this kind of lengthy language to define or to characterize the performance of all kinds of models and algorithms, because they're dependent on the input. So of course, if for two machine learning models and algorithm, like one model can give you such kind of claim based upon very small epsilon, very small delta, then it is good, right? If another classifier ends up with this claim with larger epsilon, large delta, it's not good. So this is the way how we describe the performance of your machine learning algorithm. So, and a large branch of machine learning, computational learning theory is talking about like how do I make a claim about this in terms of your empirical error. That's why we mentioned that like the true error is always not touchable, right? It's there, it's always there, but we can never reach it, right? And the easiest evaluation error is the empirical error. As long as you have the training data, you can evaluate the training error, right? So then the question is that how do we infer the true error based upon the empirical error, right? This is an important topic a large topic in computational learning theory, right? And there's a lot of like a bomb about that. We'll talk about them for a few, but just minimum sufficient for us to learn a few important methods like boosting and support vector machines. If you're interested in that, there's there's some kind of special class on it. It's not in our class, in other schools. Okay, so now let us talk about a concept called PAC Learnability. So it talks about whether a machine learning algorithm or learner can effectively or efficiently learn some particular type of function. So here's the definition. let us consider a concept class C defined over an instance space X. So concept class C, we mentioned before, is a type or family of target functions. And the instance space consists of feature vectors of length n. I mean, each instance is represented by an n-dimensional feature vector. And we have a machine learner, L, using the hypothesis space H. Right? This is a precondition. Then we can claim that the concept class C is PAC learnable by the machine learning algorithm L if for every target function inside C, and for every distribution D over the instance space, and for every fixed epsilon delta, with only a polynomial many examples to 1 over epsilon, 1 over delta, n is the feature vector dimension, and the size of hypothesis space, our learning algorithm L can produce with probability at least 1 minus delta the hypothesis that has error at most epsilon. This is kind of a lengthy definition. We can read it again to help you capture the concept. So, let me rephrase again, right? So we say, okay, the concept class C is PAC learnable by the learning algorithm L using the hypothesis space H if for every possible target function in C, and for every possible distribution in the instance space, and every possible epsilon delta, our learning algorithm, as long as use a polynomial many examples to this for numbers, it can have a very high chance, high probability, at least 1 minus delta, to produce the hypothesis that has error at most epsilon. So basically says, okay, if a learning algorithm L can very effectively and very efficiently learn this type of target functions, it means that, okay, it doesn't use many training examples. You just use a polynomial many such kind of examples. They can arrive at a specific error level under specific confidence level. Does it make sense? So this is the whole idea. But of course, if you need to accurately express everything, you have to use such kind of sentences. And again, like we call that error. True error is defined as probability that your the prediction made by a learned hypothesis is different from the true label under the stated distribution. And epsilon indicates the generalization error level, right? And delta actually represents the confidence level. Take a concrete example. If epsilon is 0.1 and delta is 0.1, what does it mean? It means, okay, my learner L have the chance at least 90% to give you a classifier whose true error is at most 0.1. So say, right? So of course, the smaller the epsilon, the smaller the delta, the better the performance, right? Indicates better performance. Say you found like epsilon to be 0.01, delta to be 0.01. That means, okay, my learning algorithm, my decision tree, or my neural nets, under 99% chances to give you a classifier whose true error is at most 1%. Means that whose accuracy to be at least 99%, right? That's really amazing, right? So this is the definition of the PAC learnability. So basically, it's just a condition to show condition to test whether a particular learning algorithm can effectively and efficiently to learn a specific type of target function. And of course, we can add an actual requirement about the computational efficiency. Right? These are talking about how many examples, right? You do not necessarily need too many examples. They are only polynomial to 1 over epsilon, 1 over delta, and the size, dimension of feature vector, and the size of hypothesis space. We can achieve arbitrary level of the generalization performance on the arbitrary confidence level, right? This is about talking about they won't use too many examples. But at the same time, you can further require that the computational complexity to produce such kind of hypothesis is also polynomial in these 4 numbers. So basically means, okay, I'm not only efficient in samples, but also efficient in time complexity. Right? This is called efficiently learnable. So now let us look at what does the PAC learnability impose, right? Actually, we impose 2 limitations, right? 2 constraints. First, we require polynomial sample complexity. Right? If your learning algorithm can be classified as good, I mean PAC learnable, right? Then it means that it cannot use too many. Its sample complexity cannot be too high. It just use a polynomial many examples to achieve the desired error level on the desired confidence level. Right? It should satisfy this sample complexity requirement on the arbitrary levels and number of samples and feature dimensions. Right? And secondly, it imposes a polynomial time complexity. These are about the computational complexity. Right? So we can see the requirement for PAC learnability is quite strong in that for any target function f at any level of epsilon delta, we can always find a hypothesis h that satisfies this probabilistic claim. That actually usually implies that we have to assume the hypothesis space is a superset of the concept class. Otherwise, it's hardly to satisfy this requirement. You can imagine that if there's some kind of non-overlapping part between the concept class and the hypothesis space, right? You can choose some kind of target function such that when you go over the entire hypothesis space, you cannot find a hypothesis which is close enough to this target function, right? That means for some particular epsilon and delta, it cannot satisfy. Then that won't be PAC learnable. So usually, to satisfy the PAC learnability, we have to assume the hypothesis space contains the concept class. And call it properly PAC learnable if these 2 species are identical. So any questions so far?
So in the definition, there's the epsilon, and the delta, and how do we know those values?
You do not know these values.
Okay.
It says, okay, you can. It said, the definition says that for arbitrary epsilon delta, you're giving, as long as it uses a polynomial many examples to these 4 numbers, it satisfies this level, then you can claim it's PAC learnable. If you can find out a particular epsilon delta such that the number of examples is exponential to this to achieve this epsilon delta level, this is not PAC learnable.
And by polynomial, what do you mean?
Polynomial means that if you write down m as a function of these 4 numbers, it must be a polynomial function. It cannot be have like any exponential term where any of these terms is in exponent.
On the next page, were we saying there's one h for all f, or are we saying for each f there's one h?
No, just for all f, H is a whole hypothesis space, right? So for every F, we have a fixed.
A different H. A different H for every F. Or
You mean small h or big H?
small H.
Oh yeah, of course,
Great.
of course. I know this concept is kind of like not very straightforward, right? But let me know where you feel uncomfortable, feel concerned. But high level is like this. It just means, okay, if I want to show that your specific learning algorithm can PAC learn some specific type of target function, you have to test all possible values of epsilon delta, whether your learning algorithm only uses a polynomial many examples to this full number can achieve this epsilon delta level. If this condition is satisfied, well, you can claim, okay, your machine learning algorithm is really good. It doesn't require too many examples.
Examples of PAC learnable and non-PAC learnable.
Right now,
Yeah.
no, I cannot give you an example.
For example, decision tree is PAC learnable.
It depends on what kind of function you're going to use. If you learn a very complicated function, probably it's not PAC learnable. So PAC learnable means that, okay, whether your learning algorithm can PAC learn B, right? You have to indicate what is the type of the target function, what is the type of machine learning model. It's not say, okay, your learning algorithm is PAC learnable. It doesn't make sense.
So if you were gonna like try to prove an algorithm or a model with PAC or a target function with PAC learnable, you just have to prove it for that one target function. You don't have to say for all of the target functions in this class.
You have to say for all functions in this class.
How could you ever prove that for all of the target functions?
There are some kind of theoretical tools and standard procedure to do that. We're not going to talk about this in detail, but I want you guys to understand this definition. Yeah, something seems kind of hard, but it's not that hard. As long as you make a proper assumption. Like for example, if you assume your classifier is Bloom function and you use decision tree, you can try to prove whether it is PAC learnable or not. Any other question? I mean, is there anyone like feel difficult to understand this definition, or everyone is comfortable with this, but just feel uncomfortable about this lengthy definition?
I guess I just don't understand a concept class. Could you maybe say what a concept class is one more time?
Yep. So I can define concept class to be linear functions.
Okay.
They could be linear functions, right? And right now I'm trying to build up a regression tree, it's not decision tree, regression decision tree. I want to know whether my regression decision tree can PAC learn linear functions. Does it make sense?
Yeah.
If I want to show that my regression tree, the linear functions is PAC learnable by the regression trees, according to the definition, what should I do?
Show that for any given epsilon and delta, your model can like produce results within there, but there's one.
Yes. It's not only on that, right? So I have to show like for every specific linear function, like ax plus b, right? Or whatever. For every 0.1 x plus 0.3 equals to 0. And for every distribution over your instance space. And then for every epsilon delta levels. I can show that with my regression tree, I only use a polynomial number of the examples to this 4 parameters. I can give you a tree with at least 1 minus delta, has an error at most epsilon. So to say, this is a very strong requirement, right? So, in other words, the definition of PAC learnability is called worst definition, a worst case definition, because it requires your learning algorithm meet its accuracy for every distribution and for every target function, and also for every epsilon and delta levels. Any questions so far?
What does it mean to be properly PAC learnable?
It just means your hypothesis space H is the same as the concept class C. Oh, this is jargon. I don't know why they define it to be properly PAC learnable.
Okay.
It's just kind of jargon, but this is equivalent to say H equals to C. Okay, yeah. So PAC learnability is a very important concept in computational learning theory, but we're not going to talk about it in depth because that will involve a lot of proof. I think it's not focused out of our class, right? But you should be aware of such concept. And when we talk about that, probably in the future you want to go deeper in theoretical guarantees of learning algorithm, you can pick it up. Okay, so now let's talk about the Occam's razor. So we briefly mentioned what is Occam's razor before, right? When we talk about how to build decision trees, suppose for a given data set you have 10 trees. Each tree can perfectly summarize the data, right? Which tree should we choose? Yeah, heard that, the smallest tree, right? And we mentioned that why we should choose the smallest tree. We said, okay, according to Occam's razor. So Occam's razor I mean, in a nutshell, it just means, okay, we should prefer simpler explanations over more complex ones. In other words, without necessity, we shouldn't increase the complexity of a model. So among all the decision trees, I should choose the smallest one because it's the simplest. If you write down a set of rules, those rules will be minimal. So historically, Occam's razor is a widely prevalent idea across different schools of philosophy. Right? But right now it's adopted by many scientific engineering disciplines, right? Especially in model choices. But right now we want to justify this principle using the concept we have just discussed in computational learning theory. Namely, based upon true error, empirical error, sample complexity, those kind of concepts, can we use math language to justify Occam's razor? This gives you a sense how those computational learning theory guys are working. Although you are not necessary to do those kind of stuff. Right? So let us first look at the claim. This claim is like this. So the probability that there is a hypothesis in a space such that H is consistent with M training examples, and the generalization error of H is bigger than epsilon, this chance is less than this number. So this number is first the size of a whole hypothesis space H multiplying with 1 minus epsilon to the power of M. So basically it's a bound in probability, right? The probability that you have a hypothesis which is consistent with M training examples, but your true error is bigger than epsilon. So why should we talk about this claim, right? So first, this is a true claim. It's no matter what kind of learning algorithm you have, as long as your learning algorithm can produce such a hypothesis, then the probability that it has this true error bigger than epsilon is upper bound by this number. It's general. It's a general claim, right? So it states the fact that if you have a consistent learner, it always produces hypotheses that perfectly fit the trained data, but the true error, the generalization performance is bad. What's the chance for that? You get the point? Does it make sense? So let me speak it again. It's a bit more abstractive. It's a bit abstractive, but believe me, it's not tricky. It's just a way to think of it. So let us look at this. First, this is a random event, right? When this event happens, two conditions. First, I have a consistent hypothesis which can perfectly predict m training examples, right? And secondly, the true error of a hypothesis is bigger than some level epsilon. Now we're talking about the probability of this event happening, right? I can tell you the probability of this bad event happening. This bad event is upper bounded by the size of hypothesis space multiplying with 1 minus epsilon to the power of n. Why we call this event as bad event? So imagine you have a very powerful machine learning algorithm, like you have a fully expanded decision tree. It ensures that every time you can perfectly fit all the trained data. That means, okay, no matter how many examples you're using, if you fully expand your decision trees, your learned decision tree, namely the hypothesis, will have 0 training error. Right? But the question is that, ideally, I want my learned decision tree, who perfectly fit the training data, can give very good true error generalization performance, right? But what if its generalization performance bad is bigger than some epsilon, right? Like I view like the generalization is bigger than 0.1 is a bad thing. So I want to know the chance of this bad thing happening. Does it make sense? Okay. So in summary, it just means, okay, if I have a hypothesis which is consistent with all training data, but its performs badly in predicting future examples, what's the chance for that? I can claim that this chance is upper bounded by this number. So to give a deeper understanding of this claim, we can try to prove this. Through the proof, you feel like more natural. Okay, so let us first assume, like here, the claim is that there is such a hypothesis. It doesn't indicate any specific hypothesis, right? We're starting from like a simpler step. We assume we find such a bad hypothesis, which is small h, right? It might be like third hypothesis in the whole space, right? So I have such a bad hypothesis that has a true error is bigger than epsilon. Then the probability that h is consistent with one training example is upper bounded by 1 minus epsilon, right? Why?
It's equal to 1 minus probability of the f of x.
Yes. Yes. Because it's the definition of the error, right? The definition of the true error is the probability that I make a wrong prediction, right? So now the probability you make wrong prediction is bigger than epsilon, then the probability that you make right prediction is less than 1 minus epsilon, right? So that means, okay, for a specific hypothesis whose generalization performance is bad but consistent with one particular example, sample from same data distribution, D is upper bounded by 1 minus epsilon, right? So now, we know the training set consists of m examples drawn independently from the data distribution. Then the probability that this bad hypothesis H is consistent with all the m examples is upper bounded by 1 minus epsilon to the power of m. Does it make sense? Right? Because it just means, okay, the event that H is bad but consistent with training example 1, and H is bad but consistent with training example 2, blah, 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 until H is bad until the last training example. H is bad but consistent with the last training example, right? So those events are independent. So the probability of their union of their intersection is upper bounded by 1 minus epsilon to the power of n. Does it make sense? So we'll arrive at a second conclusion that the hypothesis H is bad, but consistent with M example is less than 1 minus epsilon to the power of m. You just multiply the left-hand side for m times, you got this, right? And the upper bound by m times, you got this. Does everybody feel comfortable? Or someone feels confusing about this? You just apply the statistic knowledge we have learned before. Okay, if you feel uncomfortable about this, don't hesitate. After class, come to my office hour. We can go through it again. Right? So now we have a simple claim that for a bad hypothesis means that okay, this true error is bigger than epsilon, but it happens to correctly predict all the training examples. This chance is upper bounded by 1 minus epsilon to the power of m. But this is not the original claim. The original claim means that okay, there exists such a hypothesis. But here we are talking about okay, H is here. Then how do we draw a connection between the two claims? So our question would be like, what is the probability that there exists some bad hypothesis in H that is consistent with all M examples? How can I draw the conclusion based on this?
Union probability.
Yeah, perfect, right? We should review this event. We should look at the structure of this event, right? This event, we're talking about, this claim is talking about the chance of this event happening, right? This event is that, okay, there exists some bad hypothesis in the hypothesis space that is consistent with all the M training examples, right? So we know that this event can be decomposed as a union of set of independent events. What is it? We just enumerate all possible hypotheses in the space, right? So the event A happens means that the first hypothesis is bad, but consistent with M examples. Or the second hypothesis is bad, but consistent with M examples. Or blah 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 until or the last hypothesis is bad, but consistent with all the M examples, right? This is the definition of this event. Does it make sense? Right. So let's look. Let me describe it again. Right. Even A means okay. Even A says okay. There exists some bad hypothesis that is consistent with M examples, right? So how can we represent this event? When will even A happen? The first event. That means okay. This event might be the first. This bad hypothesis might be the first hypothesis in the space. Might be second, might be third, might be the last one, right? We have all kinds of possibilities, right? So we can represent this event as a union of set of events. Right? Each random event will be some specific hypothesis in the space is bad and consistent with the M training examples. Okay? Yeah, let's try to memorize or remember what we have done for the homework 0, right? This is useful to the homework 0. So it's just definition of the set representation of events, right? So if we denote each independent event here, meaning each specific hypothesis is bad, but consistent with M examples as B1, B2 to B size of H, then we can represent this event A as a union of B1, B2 to B size of H, right? Then, according to the inequality you guys have proved in your homework 0, we know the probability of A is upper bounded by the summation of each probability in B1, B2 for B1, B2 to BH, right? So we know the probability of B1, B2, or B3, each of them is actually the probability that some specific hypothesis is bad, but consistent with m examples, and is upper bounded by 1 minus epsilon to the power of m, right? So just adds up all the upper bounds. We have a size of h upper bounds adding together, right? So now we arrive at this conclusion.
Why are the events disjoint from one another? Like B1, B2, B3.
Disjoint.
Why are they?
We're not talking about their disjoint.
Oh, okay.
B1 is just one even, right?
Okay.
So B1 or B2 does not mean B1 and B2 are mutual exclusive,
Yeah.
right? It could happen both.
Okay.
So that's the definition of union. If you want to say, if you want to say mutual exclusive, it's not union, it's not intersection.
Okay.
It's actually other operations. You have to use other operations.
But you're adding up their probabilities at the bottom, right?
Yes. And this inequality, it appears in a homework 0.
Okay.
Right? If you can represent some even A as a union of set other events,
Yeah.
then you can claim that the probability of A is less than or equal to the summation of probability of each one in the union.
Thank you. Yeah.
Right.
Yeah.
Okay.
We should to the left hand side.
Yeah. We should do the homework 0 right now. Not at the beginning, right? Okay.
Thanks.
Any other question? Oh, it's too straightforward. 0 not comfortable. Okay. Again, if you still feel uncomfortable, we can go through details later in the office hour. Okay. So so now I have proved this claim, right? So basically says that the probability that there exists a hypothesis in a hypothesis space that is consistent with all the M chain examples, but the generalization performance is bad. This chance is bigger, is upper bounded by the size of hypothesis space multiplied with 1 minus epsilon to the power of m. So imagine you have a very good classifier, which you believe is very good, right? And every time it can find out hypothesis which perfectly fit the training data, meaning your training error is 0. Of course, you expect the true error, the generalization performance of your learned classifier is very good as well. But there is some chance that your learned hypothesis performs better. For example, its generalization error is bigger than 0.2. It's some kind of things I feel unacceptable, right? If I were a machine learning algorithm designer, I want this event to have the smallest chance to happen. I don't want this event to happen at all. But again, this is a random event. You cannot forbid its occurrence, right? It always has chance to happen. Then the question is that, can I control its chance to happen under some level? So I say, okay, I accept the fact that no matter how powerful my neural network is, I always have a chance to end up with very bad neural networks. Right? But I want this chance to be as small as possible. Say I want to control this chance to be less than 0.01. Or 99% case, my neural network is really good, but I allow in a 1% case to end up with very bad neural nets. How can we do that?
Choose a particular M besides the one.
Yes.
Set that.
Yes. Intuitively, you can imagine that if I can increase the number of training examples, right? The more training examples you have, the lower such kind of chance it happens, right? In the extreme case, suppose your number of training examples is so large it covers every instance in the instance space. This kind of chance will never happen, right? Because in practice, it's never possible. So then, how many examples do we need to use to make this chance to be under some specific level, say delta?
Thus we can say that one is less than delta and H log and
Yes.
delta.
Yes, exactly right. So now we know the bound, the upper bound of this bad event happen is this number, right? So now, if I want to control the chance of this event to be less than some delta, I just solve this. I just to suppress this bound to be less than less than delta. That's it, right? So if we want to make this probability small, say smaller than delta, then we just solve this upper bound. The inequality that this upper bound is less than delta, right? Then the question is that how can we solve this inequality in terms of the number of training examples n? And when number of training examples satisfy this inequality, we can safely say, okay, I end up with a consistent neural network, but performs badly. This kind of event has very low chance it's below delta. Right? That's the idea. Any question?
What is size of H?
What?
H. Size of H.
Yeah, H here we just assume we know the size of H. Okay, so the question is that how can we solve this, right? So we can take a logarithm on both sides. We have a logarithm size of H multiplying m logarithm 1 minus epsilon is less than logarithm of delta, right? Delta is some specific level I gave, right? Then this part is still a bit complex to solve, and then we introduce another upper bound. Use this inequality. We have a logarithm of 1 minus epsilon is less than minus epsilon. So we use this inequality to construct an upper bound for this. So basically, I got this inequality. I got this upper bound. So this upper bound is bigger than the left-hand side, right? So I can solve this new inequality instead. Why? Because if this happens, then log delta must be bigger than this, right? That means, okay, I can get even safer number of training examples n to satisfy this inequality. Right? And then the remaining thing is that to solve this is pretty straightforward. You can move m minus epsilon to the right hand side and move logarithm delta to the left hand side and solve it. You get m epsilon is bigger than this, and divided both sides by by epsilon, you end up with this. So now here's the result we get. If the training example m is bigger than 1 over epsilon, multiply with logarithm size of hypothesis space plus logarithm of 1 over delta, then we claim that the probability you're getting a bad hypothesis is smaller than the designated level delta. Does it make sense? Any question? Of course, someone will question that, okay, why do you use this, right? And that means, okay, this bound is really, really loose, right? You might waste a lot of examples. But here, we just do theoretical analysis. You may, I mean, in practice, you might not necessarily use so many examples because you continue to upper bound the left-hand side, right? You might use even less examples to make your probability that you end up with bad hypothesis to be smaller than delta. But here it's just theoretical trick. It's just to give you this bound to expect some kind of information and insight of that. Any questions so far? Okay, so now let's look at the conclusion we have derived. So we can list it in this way, right? Let big H to be any hypothesis space. Then we can claim that if the number of training examples is bigger than this lower bound, then with probability at least 1 minus delta, the hypothesis H that is consistent with the training set of size m will have true error less than epsilon. In other words, if your machine learning algorithm, we call it consistent learner, is guaranteed to produce a hypothesis has 0 training error, as long as the number of training examples you feed to your learner is bigger than this, you can guarantee with high chance, at least 1 is delta, your learned hypothesis has true error at most epsilon. So this is also characterized as sample complexity. Right? So how many examples does your consistent learner need to achieve some designated error level and confidence level? Does it make sense? Okay, so now let us look at this bound. Right? What does this bound reflect? Is this bound informative? Right? Is that something we're concerned about? Because right now we're doing like qualitative analysis, not quantitative analysis. Right? We actually do not care how many exactly the number, right? 100 or 200, it doesn't matter. We just care about what does this bound reflect. Right? So first, we know this bound is proportional to inverse of epsilon. This sounds very reasonable, right? Epsilon is the error level, right? The smaller epsilon, that means, okay, the larger the bound. That means the smaller you expect the true error, the more examples you need to provide to your machine learning algorithm, right? You cannot expect that, okay, I use 10 examples, I get like 0.001 test error. It's not possible. There's no free lunch. And second term, we see that, okay, the requirement for number of samples is also determined by the size of hypothesis space. It means that, okay, for the same epsilon and delta, if I want to chain the same epsilon delta, right, the algorithms which have a larger hypothesis space will need more training examples, right? The larger hypothesis space your algorithm use, the more complex your machine learning model is. Okay, that means, okay, the more complex models you choose, the more training examples you require. So see, this is reasonable as well, right? If I use linear regression, well, I don't need that much training and that many training examples to achieve some specific level. Right? But if you use artificial neural nets, well, you have to use a lot of examples. Right? And the last term is about the confidence level. If I want a higher confidence level, that means, okay, my delta to be even smaller. That means you have to give more training examples as well. The more training examples you use to train a classifier, the more confident you are about the performance of your classifier, right? So now I want to ask, which term reflects the Occam's razor? Think about it.
The contact is not operates.
Okay. Why?
But it's the size of the space that we want to search over.
Yes. And your
Pretty much the same I was going to say. As we add complexity, we need more data.
yeah. So here, the justification of Occam razor comes from here, right? So say, as we just mentioned, right? We will have like a bunch of models, right? And to achieve the same error level and confidence level, the more complex models requires more training examples. That means we favor simpler models, right? This is consistent with Occam's razor, right? Occam's razor requires the same, prefers simpler models, right? And you can view it on the other side. Let's suppose like I have 10 models where the number of training examples are fixed. It's just 100. Right? Now I train each of those models with these 100 examples. Right? from this lower bound samples, which kind of model will achieve better epsilon delta? In other words, which kind of models will have a smaller epsilon, smaller delta? M is fixed here, right? I have a bunch of models, and different models have different size of H, right? So here, this term, if it is larger, if you want to satisfy this inequality, you have to make epsilon delta be larger as well, right? So that their inverse is smaller. So that means, okay, given the same fixed number of training examples, complex models will end up with a worse claim about the error level and confidence level. This is another way to view the Occam's reason. If you provide the same training set, right? So usually the simple model will end up with a better generalization performance. That's what we can say from this model. Does it make sense? Yeah, this is probably, I mean,
Can you talk about the third term, the natural log of 1 over delta? I'm very confused about that.
you want to what?
I'm a bit confused about that third term. Is delta the
Delta is between 0 and 1. So 1 over delta must be bigger than 1. So it's positive. Don't worry about that.
So if you make your model more complex, why does that increase the hypothesis space?
Oh, that's the common practice. The more complex your model usually means the hypothesis is larger. So remember, the learning algorithm, the learning procedure is essentially a search procedure. Right? So what is the more complex search procedure? That means, okay, you search over larger hypothesis space. That's our tradition to differentiate the complexity of different machine learning models. Because the search itself, I mean, from discrete perspective, it's just numeric, right? From continuous perspective, it's gradient descent. So we won't consider like if you're using gradient descent to be more efficient than using any other methods. We're talking about the space you're searching over. The larger space you're searching over, the more complex your learning algorithm is. Does it make sense?
Yeah.
Any other question?
What's the hypothesis space in decision tree?
It depends on what type of feature vectors. What type of if a feature vector is binary, you can imagine what is the hypothesis space.
For example, one we had in the lecture about outlook, temperature, and in that example, what's its hypothesis space? It's a binary.
The hypothesis space means that the set of functions it can learn. Like you can think of what set of functions it can learn. I'll give you a conclusion for if your instance spaces are binary feature vectors, then the hypothesis space are all possible binary feature vectors. So decision trees are very complicated models. So actually, you can show that for any set of training examples with binary features and binary labels, you're always able to build decision tree to perfect fitting. That means you can fit all kinds of binary Bloom functions. So the hypothesis space is quite large, but there are many other, like if you use the linear classifier, it now covers all the Bloom functions. Like XOR, it cannot cover. what is going deeper than we expect, because previously I set up a few classes to have a deeper discussion, but it's not very popular.
So do you have a decision tree and then you like trim on nodes that decreases your hypothesis space because you trim it?
Yep.
Okay.
That's another way to justify our strategies to do the pruning, right? We intentionally, like the simplest strategy is to control the growth of the tree, right? I set the maximum depth, right? You set maximum depth, that means you cut a lot of like hypothesis, right? You reduce the hypothesis space. That means, okay, you have a smaller. Does it make sense? Any other question regarding this? Yeah, if someone, I mean, if anyone are interested in like talking about more in depth about this, right? I have some more content about that, but not covered in this class. You're welcome to come to my office or Occam. But from this simple claim, right? It's a very idealized situation that you have machine learning models. Your learning algorithm always produce a consistent hypothesis space. This is actually not practical in real world, and we have this sample complexity which reflects Occam's reason. This is kind of amazing stuff. Right? So also we can connect our consistent learners with Occam's reasons under the PAC learnability, the definition of PAC learnability, right? So if I have a consistent learner, I'm given a training set of M examples, right? How can I justify my consistent learner is PAC learnable? I mean, PAC learn the specific concept class. First, we can see whether M is large enough, right? And then we can test this bound using different epsilon delta, right? For any epsilon delta which satisfies this bound, we can claim, okay, my learned hypothesis has achieved a true error at most epsilon with probability at least 1 minus delta, right? So you can just look into this bound. And also, you need to check whether M to be too large, right? Remember from the definition of PAC learnability, we want M to achieve the specific level of epsilon delta. M must be polynomial in 1 over epsilon 1 over delta size of H and the number of features. So from this bound, we say, okay, this bound is very friendly, right? It's already polynomial to all those numbers. For this term, and this term is even like sub-polynomial. It's even better than polynomial. But you need to check whether M is polynomial to the feature dimension, the input of features. And finally, if you want to show this efficiently PAC learnable, you have to also see whether time complexity is polynomial to the 4 numbers we mentioned before. Okay, any question so far? Again, the requirement for this topic is, I mean, for you guys, is to understand this kind of unintuitive definition. But you need to know why it is defined like that, why it is used such tedious languages to characterize the performance, and how we end up with this sample complexity. From a mathematical perspective, I don't believe this is, extremely tricky. But you need to go through it and to understand their logic and their inner logic to derive such kind of conclusion. Then you have a deeper understanding of how we characterize the performance for any machine learning algorithm. Okay? Okay, great. So our next topic will be will be ensemble learning. So we now return to practical world. Ensemble learning. So it's a very widely used, very successful, very classical machine learning strategy. So it reflects the philosophy that two heads is better than one. So the strategy is to combine a set of crappy classifiers together using a smart way. You end up with a very strong classifier. It's called ensemble learning. So we mainly focus on two strategies to conduct ensemble learning. One is called boosting, and the other is called backing. So what is boosting? We'll introduce what is boosting, the concept of boosting. And then we'll introduce probably the most popular boosting algorithm called ADA boost. And is implemented in digital camera, in many applications, right? And finally, we'll introduce the backing methods. So what is boosting? So the general idea of boosting still comes from the theoretical machine learning, namely computational learning theory. So don't complain, it's boring, but it's really useful. So it's a general learning approach to construct a stronger learner, given a collection of weak learners. And in theory, we can say, okay, we have like infinite number of weak learners, but in practice, we always have like a finite number of weak learners. Right? So historically, boosting was proposed to answer the theoretical question in PAC learning. So this is the link. This is the pioneer paper, the seminal work made by Robert Shapiro, who was a professor in Princeton for many years. He's now in Microsoft Research. He's a pioneer of this series of learning algorithms. So boosting is a way to create a strong learner using only weak learners, also known as rules of thumb. And but ensemble method is a kind of broader concept. It means a class of learning algorithms, including boosting, that composes classifiers using other classifiers as building blocks. Like I use decision trees, very shallow decision trees. We know it's weak, right? And we just combine a bunch of shallow decision trees, and now it's very complicated, very powerful ensemble of decision trees. And boosting has stronger theoretical guarantees than other ensemble methods. That's why we first introduced boosting. So here are a list of examples where the boosting algorithms are applied with this detector we mentioned before. Right now, if you use digital camera, you take a picture. Before you take a shot, every feces inside your camera will be bounded. Right? It's quite accurate and very fast. So that was implemented by AWS. And from after our class, you should be able to implement such algorithms by yourself. Right? And handwritten letter recognition, text classification, use tagging, information retrieval, motion capture. Like when the camera record the video, and when some people or some objects do some sound motion, it's very important to capture the motion because in many accidents, it's important to capture the moment that accident happens. Right? It's called motion capture. And DNA sequence analysis, a lot of other applications. So here I want to introduce the formal setup for boosting. So I want to define what is strong PAC algorithm and what is weak PAC algorithm. So strong PAC algorithm directly comes from the definition of PAC learnability. So we call a machine learning algorithm a strong PAC algorithm if for any distribution over the training examples and test examples, namely the instance space, right? For every designated epsilon delta, it uses only a polynomial many random examples to find a hypothesis with true error less than epsilon with high chance at least 1 minus delta. So just copy the definition from the PAC learnability. But correspondingly, we have the definition for weak PAC algorithm. So what's the definition of weak PAC algorithm? The major difference is that we cannot specify arbitrary level of some epsilon. So for strong PAC algorithm, I can set epsilon to be 0.01, 0.0001, right? Arbitrary level epsilon can be set. But for weak PAC algorithm, epsilon has some lower bound. It cannot be arbitrarily small. Instead, it has a lower bound of half subtracted by gamma. So gamma is positive number. And usually gamma is to be very small. It means that your weak PAC algorithm is just slightly better than a random classifier. Say a gamma would be 0.1, right? So that means epsilon is no less than, is bigger than or equal to 0.4. That means, okay, no matter how many training examples, that means no matter how confidence level you're given, and for any distribution, for any polynomial number of training examples, your true error is at least 0.4. That's not good, right? So random classifier is 0.5. You randomly draw a coin and say if it's head or tail. Right? It's head, okay, I predict it's positive, otherwise negative. You can expect the performance is 0.5. And the weak PAC algorithm says that, okay, I'm just slightly better than throwing a coin. Probably 0.4, 0.45. Then the question is that, can we use a weak PAC algorithm to derive strong PAC algorithm? More formally, can we, does weak learnability imply strong learnability? And the answer is yes. So that's very interesting, but here I just give you historical lines on that. In 1989, Shafir first provided the first probable boosting algorithm, and they call a weak learner 3 times on 3 modified distributions got slightly better performance. So I'll apply recursively, but this is just, it's very theoretical meaningful, but in practice, people won't see any advantage of using boosting. And then in 1990s, Krohn proposed the optimal algorithm that boosts by majority. Like how do you combine a set of weak learners? How do you combine them? They call it boost by majority. And we'll mention what is boost by majority. And then in 1992, they do the first experiments using boosting, and they're limited by practical drawbacks. So not practical at all, but in 1995 is a breakthrough. So these two people introduced the EDA boost algorithm. It's so powerful and so amazing. And then it makes a hot research area for quite a long time, right? So it has a strong practical advantages over previous boosting algorithm. So, and then the EDA boost was followed by a huge number of papers and practical applications. And in 2003, Freud and Sheffield won the Goldel Prize, which is the best prize, best award, and most prestigious award in theoretical computer science. Okay, I think we should stop here, and let us continue.